everybody. Hope you're all healthy and safe at home. It's been a while that I have uploaded a session. So let us continue with our functional analysis. We are going to begin with the next module, that is module 2, Hilbert spaces. In the previous lecture, we had discussed about norm spaces and all. So now we are moving on to the discussion of Hilbert spaces. So let us see what is meant by Hilbert spaces. But before going into the actual definition, now we know how we had come to the definition of norm space. First we had defined what a norm was, then we had considered about the norm space. So in a similar manner, here first we are going to discuss about the concept of inner product. Now let H be any linear space over the complex field. Then the inner product is basically a function which accepts two variables, that is inner product. We denote it by the bracket of this form. Inner product is a function from H cross H to the complex field to C, and it should satisfy the following three properties. So let's see the properties one by one. The first one is inner product XX should be greater than equal to 0, and inner product XX is equal to 0 if and only if X is 0. The second one, inner product AX1 plus BX2 Y is equal to A into inner product X1Y plus B into inner product X2Y. And the last one is inner product XY conjugate is equal to inner product YX. So if you see, we are mapping it to the complex field. So the conjugate, we can consider the values inner product will be a complex number. So you can consider the concept of this conjugate and all. So if you see the first two properties, you can see that there is, if you remember the properties or axioms which are to be satisfied by the norm function, they are almost pretty much similar. So in the later classes and all, we can see that there is a relation between the inner product and the norm function. Now there is something that I would like you guys to note, that is using the third property, that was the conjugate property, that is inner product XY conjugate is equal to inner product YX. Using that property, we can obtain the following, that is inner product X comma AY1 BY2 is equal to A conjugate inner product XY1 plus B conjugate inner product XY2. So let us see how we can formulate that. It is pretty much simple. What do we have to show? We have to show that inner product XAY1 plus BY2. We need to find what is this actually, right? Now using the property of inner product, we know that inner product AX1, that is it is linear with respect to the first variable, right? We had seen that this can be written as inner product A into inner product X1Y plus B into inner product X2Y, right? So using this axiom or property and the property that inner product XY conjugate is equal to inner product YX, using these two properties, what we'll do, we'll prove the above equation. So we have, let us see, we need to show that, let's consider inner product XAY1 plus BY2. Now using the third property, we know that this is same as AY1 plus BY2 conjugate, right? Inner product X AY1 plus BY2 is equal to inner product AY1 plus BY2 X conjugate. Now we know that it is linear with respect to the inner product is linear with respect to the first variable. So we can take A conjugate inner product Y1 X conjugate plus B conjugate into inner product Y2 x conjugate, right? So we have used the second property. Now again using the third property, what do we get? We get inner product. This y1 x conjugate is nothing but x inner product xy1, and again this will be inner product xy2. So we have obtained that inner product xay1 plus by2 is equal to a conjugate inner product xy1 plus b conjugate inner product xy2. So this property is also called as the conjugate linearity of the inner product. So that was very easy to prove. Now I had stated in the previous slide that there is a relation between the inner product and the norm. So you can see that if you consider a function p of x is equal to inner product xx raised to 1 by 2, okay, that is inner product xx raised to 1 by 2, then we can easily see that that function p of x is a norm, that is it satisfies the three properties of the norm. So we will deal with it in the following classes. So there are some examples which are given in your textbook, which I would like you guys to verify. Let's just go through the examples. The examples are, if you consider the space Cn, it is complex tuples, we are defining inner product xy is equal to summation ai bi conjugate, okay, where x and y are n tuples. So we are considering the inner product xy is equal to summation 1 to n ai bi conjugate. So this will satisfy all the three properties that we have mentioned above. And in the space L2 we are defining again it is same, except that in Cn we had considered the finite tuples, in L2 it will be infinite tuples, that is summation I equal to 1 to n ai bi conjugate. And we can use the application of Holder inequality to show that this is satisfies the properties. Also using this same, we can easily see that inner product xy is less than or equal to norm x into norm y. Here just note that here norm x is actually, we are considering it to be inner product xx raised to 1 by 2. You can do this after we discuss the relation between inner product and norm also, but you can easily verify that the inner product which we have defined in example 1 and 2 satisfies all the properties of the inner product. Also there is another example, that is in the space of all continuous functions on A to B. We can see the inner product will be defined by inner product f comma g is integral a to b f of t g of t conjugate. Instead of summation we have integral a to b. This also you can easily verify that it is it satisfies the properties that we have mentioned in the previous in the above the properties that we had seen. So please do verify all the examples that is given in your textbooks. So that's it. We will wind up with our section. So thank you. Stay home and stay safe.